Welcome to the session. So today I am here to discuss about what is the time complexity and what are the different notations to represent time complexity. Nothing but asymptotic notations. So in the earlier session we have discussed about space complexity and how to find out the space complexity to the two different kinds of algorithms. One is non-recursive algorithms, another one is recursive algorithms. So in the today's session we are discussing about how to find out time complexity for given algorithm. So what is the definition of time complexity? The amount of time is required to execute a given procedure, or what is the set of instructions we have written. So that is called as time complexity. And to get efficient algorithms, the time complex should be minimized. Means the time complexity should be optimized. So with a less amount of time complexity, we need to get the maximum. Means efficient algorithms we may get. So first, the time taken. So the time complexity means the time taken by a program P is the sum of compile time and run time. Simply we can define as T of P is equal to C plus Tp of I. In the earlier case also we are finding the space complexity S of P is equal to C plus Sp of I. Means space complexity with reference to instance characteristic. Similarly here, time complexity of a procedure is equal to C plus Tp of I. C is nothing but the amount of time is required to execute the program at compile time. Means what are the instructions we are evaluated at compile time. So that is the C. And time complexity at runtime you are called as Tp of I with reference to instance characteristic. So here whenever we need to find out the time complexity, we need to calculate the what is the amount of time is required compile time, at the same way runtime. Next, the compile time does not depend on the instance characteristics. Means that it doesn't depend on the inputs. So already it is a fixed amount of time to run different type of test cases. Next, also we may assume that the program will be run several times without recompilation. Means once the compilation is done, no need to compile again and again, directly we can run and execute the program. That's why we are thinking that compile time is a constant. Compile time is constant. Next, consequently we concern ourselves with just the runtime of a program. Means this runtime is denoted Tp of instance characteristic. Means majority of the cases we need to calculate the runtime. Runtime. Only the time complexity. Why? Because the time complexity of a procedure is purely dependent on the runtime instance characteristics only. Next. A program step is usually defined as syntactically or semantically meaningful segment of a program that has an execution time that is independent of the instance characteristic. Means that here to find out the time complexity, two different kinds of methodologies are available. One is to declare a count variable. The count variable is incremented recursively, means iteratively, where we are identified program steps in the given task. Or that is a one method, and another one is step count method. So whatever may be the techniques, what is an outcome is to identify programmable steps. The programmable steps are having some kind of operations like assignment operation, addition operation, multiplication operation, division. Like that, one kind of operation is happened, then only consumes some time to perform the particular operation. So what are the operation related steps? Those are called as program steps. So by using two different methods, we need to calculate how many number of programmable steps in the given algorithm. Right. Next. So for example, let us consider the statement in the following algorithm. So here only one statement is there. The one statement consists of, so totally 6 additional statements are there, and one multiplication statement and one division statement, one subtraction. Right. So whatever may be the operations, totally how many program steps means the entire statement is considered as only one step. Only one step. So here for evaluation purpose it takes 1 unit of time, and the return statement saves the value into certain particular variable. For that it takes 1 unit of time. So totally by considering these two, what is the time complexity of the earlier example is simply we can say as big O of 1. Big O of 1 means constant time complexity. Constant time complexity. It means that no instance characteristics in the procedure. Why? Because each and every time they are passing 3 values A, B, C. Based on the A, B, C, we are doing the particular equation. Means we are calculating the particular equation. Means that there is no instance characteristics. There is no variation. Suppose in this example you can identify and you can clearly understand what is an instance characteristic. What is an instance characteristic? So here there is no count for open brace and closure brace. Means before going to the step count method, we need to have some idea about which ones are considered as program steps, which one as counting as step count as 1, which one doesn't have step count is 0. Right. So majority of the cases open brace, closure brace treated as a block. So open brace, closure brace, these two statements are not an executable statements. Doesn't take any time. So these two are not considered as a program steps. Step count will be assigned to these two things are 0. That is the mean of no count. Next, each basic statements like assignment and return have a count of 1. Earlier example also return statement is there. I told that for return also 1 unit of time, for calculation also 1 unit of time. So totally 2 units of time is required to perform the task, overall task. So here also for assignment is 1 unit of time, step count is 1, and for return also 1 unit of time. Next, if a basic statement is iterated then multiple by the number of times, the loop is run. Means if for these are having some conditions, the conditions are also called as expressions. The expressions means for an executing an expression the count is 1. In case of iterative statements, the for loop iterates some n number of times sometimes. So based on the frequency, we are identifying that step count into frequency. That is total number of steps for the for loop. Next, so the loop statements is iterated times, it has count as n plus 1. Why we are called it as n plus 1? Say, for suppose this is the case 1 to n. So an array having, say suppose 5 is the size, we can talk about 0 to 4 is the index, 1 to 5 is also index. So according to my algorithm, the index is 1 to 5. Okay. So 1, 2, 3, 4, 5. So the algorithm to find sum of an array of elements means that here say elements are like this. So we need to add all the elements. Right. So for I is equal to 1 to n means 1, 2, 3, 4, 5 all are the valid indexes. when the value becomes, means when the index becomes 6, then only come out of from the loop. So when the index becomes 6, means the I value is incremented 6 times, not 5 times. Initial I value is 1, later 2, later 3, later 4, later 5, later 6. Means that 5 times true, 5 times true, 1 times false. False is nothing but when I become 6, then only it is false. So that case is also considered. So totally n plus 1 times the loop is iterated. Means n plus 1 times condition checking is happened. N plus 1 times the increment is also happened. Okay. So that's why n plus 1. Here the loop runs times the true case and a check performed for the loop exit. That is also false condition. So n times true, 1 times false. Totally n plus 1 times condition is checking. Right. So this is an algorithm. So for this, step for execution is 0. This will be not considered as a program step. This is a comment, we know that step for execution is 0. This is open rest, this is also already discussed. This is also not considered as step for execution, means program step. So that's why step count is 0. Next, sum is equal to 0.0. This will be considered as program step. Why? Because here assignment statement is there. So for an assignment statement, step count is 1. How many number of times initialized? Only 1 time. That is called frequency. 1 into 1, 1. So what is the value here is 1 into 1. Totally 1. Next. So for I is equal to 1 to n2. Here condition checking is n plus 1 times. But evaluating the expression is 1 time. Means step for execution is 1. So 1 into n plus 1 is n plus 1. Next, sum is equal to sum plus a of I. Means that step for execution is 1. The frequency is n. So 1 into n, n. In case of written statement also we have discussed 1 unit of time. So step for execution is 1. Frequency also 1. 1 into 1, 1. So close brace, we have not considered 0. So totally, so 1 plus n plus 1, n plus 2 plus n, 2n plus 2 plus 1, 2n plus 3. So this is the total number of steps. So when we are receiving that TP of, actually here the P is called addition. So T of addition, procedure name is also I am including. T of addition. Where is the instance characteristic? So sometimes you are passing 5 array elements, means 5 elements. Sometimes you are passing 100, sometimes you are passing 1 lakh also. So the size is depends on purely n. So the instance characteristic is n. So T addition of n is greater than or equal to 2n plus 3. Means we are calculating the only runtime. That is mean of TP of I. Time complexity with reference to instance characteristic. So here 3 is constant, 2 is constant. So value depends on n only. So that's why the time complexity of this procedure we are talking about big O of n. Big O of n. Why we are calling big O omega theta? That is the next concept. Today only, in this session only we are discussing that. Okay. So big O of n is the time complexity for the algorithm. This is the and next. So this is a one more example. So this is the very important question. Addition of the matrices, multiplication of the matrices, they are asked nearly 4 to 5 times. Okay. So how to find out the time complexity for addition of 2 different matrices? So this is an algorithm. So already we have discussed for this step for execution 0. This is a comment line 0. This is also comment line 0. For the comment lines, heading statements, not considered as programmable steps. Open brace also not considered as programmable step. So for I is equal to 1 to n do. Okay. So in this case, the step for execution is 1, but the loop iterates m plus 1 times. Why? Because m times it is a true case, 1 time it is a false case. M times it is a true case, 1 time it is a false case. That's why 1 into m plus 1. This is the mistake only. Next, for j is equal to 1 to n do. Okay. So again 1, step for execution is 1. So this is the nested for loop. So here I already told that m times true means that the for loop executed m times. That's why m. But this for loop n times true, 1 times false. That's why n plus 1. The outer loop for loop true cases is m. The inner for loop n number of times true, 1 times false. That's why m into n plus 1. So that totally mn plus m. So this total statement. So m times executing the for loop. Here the inner for loop n times true. So totally n times into m. So mn times. So 1 into mn. So mn. So finally mn plus mn, 2mn, m plus m, 2m plus 1. So totally the equation means T of procedure name, add matrix. What are the instance characteristics for this algorithm? Here 2 different variables are there. M is a one variable, n is another variable. So m comma n. M comma n. Okay. Greater than or equal to, this is the thing we have to write. 2mn plus 2m plus 1. Okay. After that, so 1 is a constant, 2 is a constant, 2 is a constant. So totally the remaining thing is mn plus m. By considering mn plus m, mn is the maximum value. Each and every time mn gives the more value. Say for example, the given matrix is 10 by 10. M value is 10, n value is 10. 10 into 10, 100. But m value is 10. Means 100, 10. Which one gives the more value? Mn. So mn refers to the more. That's why simply we can say the time complexity of the certain procedure is big O of m into n. Right? So this is the one more example which is related to time complexity. This is the last example which is related to time complexity. So this is also one kind of approach to find time complexity. Means in the earlier cases just by using table. So in the beginning phase we need to write a table to avoid the confusion. So once you are practiced nearly 3 to 4 programs by using a table, after that in the later case directly you can assign the step count by writing the algorithm directly. No need to draw a table. Right. So this is the problem for Fibonacci series. I think you know the Fibonacci series means 0, 1. So when we are adding 0 plus 1, 1, 1 plus 1, 2, 1 plus 2, 3, like that it generates the series. Right. So for this step count is not assigned. For this step count is not assigned. If n less than or equal to 1, condition checking is there, step count is assigned, that's why 1. Next, output n, not considered as a programmable step. Else is also not considered as programmable step. Why? Because already condition checking is happened. Here we are considering as 1. So we need to consider again. F2 is equal to 0. Assignment statement. That's why 1. F1 is equal to 1. Consider as assignment statement 1. So loop for I is equal to 2 to n 2. So say or suppose n value is 3. What are the possible values here? Means 2, 3. Suppose n value is 4. What are the possible values? 2, 3, 4. Means how many times the loop is iterated, we need to check. So n times is iterated. Why? So when n value is 4, the 5 is also done. So n value is 4. So 4 different values. Okay. N value is 3, 2, 3, 4 is the false case. So again, for n value is 3, 3 times the loop means the expression is evaluated. So that's why n. Next, this is not considered here. So n times loop is iterated means that n minus 1 times true, 1 times false. So all the internal statements are executed n minus 1 times. That's why n minus 1. This is also n minus 1. This is also n minus 1. All are considered as programmable steps. Why? Because all are the assignment statements. All are the assignment statements. Next, this will be not considered. So note, output of f, here 1. Why we are considering output of f at this time, output of n we are not consider is, generally here we are storing the value into f. We are storing the value into f. That's why we are considering as 1. So totally, the considering total thing is 4n plus 1. 4n plus 1. Means how to represent this? So T of Fibonacci of instance characteristic is n greater than or equal to 4n plus 1. What we are doing? 4 is constant, 1 is constant. So totally you can say the time complexity of this operation is big O of n. Time complexity of this operation big O of n. So this is the last example which is related to time complexity. So till now we have discussed the 3 different kinds of algorithms. Okay, one is a simple algorithm. Second one is addition of sum of an array of elements. The next thing is addition of 2 different matrices. The next thing is Fibonacci series. So next we are moving to amortized time complexity. What exactly the mean of amortized time complexity? So till now the performance analysis is over. So in the performance analysis mainly we are talking about 2 different kinds of metrics, that is space complexity and another is time complexity. So amortized time complexity means sometimes suppose you have written some program, the program may have 10 steps, but in the 10 steps only 1 or 2 steps are taking more time. Based on the 2 or 3 statements, the entire time complexity is degraded. In that case, amortized time complexity comes into the picture. It gives some set of techniques to apply for finding time complexity. So here this analysis means this analysis is used to when the occasional operation is very slow, but most of the operations which are executing very frequently and fast. Means sometimes what are the statements are taking more time, here we are considering as slow. The rest of these statements are executing faster. Say for example, in our algorithm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like that, this many number of statements are there. Suppose 3 takes more time, 7 takes more time. Based on 3 and 7, the total time complexity is high. Okay, that is the case. So which are extremely very frequently and faster. In data structures, we need amortized analysis for hash tables and disjoint sets. We know one beautiful data structure here is hashing. We know that the search time complexity of a hash table is very, very less, constant amount of time complexity, that is big O of 1. Why? Because when we are substituting one element into the hash function, directly it releases some key. So in the key position, directly element is existed. So that's why the time complexity is big O of 1. But suppose it releases the key, but in that particular key position, some other element is there. Why? Because maybe the duplicate keys are happened. So for avoiding the collisions, that is called duplicate keys is nothing but collisions. So when the collisions are happened, so we need to apply the collision resolution techniques. So when we are applying the collision resolution techniques, hashing data structure doesn't give the result, the search time complexity is big O of 1. At the time it goes for big O of n. So in that case, only based on the collision resolution technique procedure only, the total time is degraded. Total time is degraded. Okay. So the same thing in the hash table, the most of the times the searching time complexity is big O of 1. Okay. But sometimes it executes big O of n operations. When we want to search or insert an element in the hash table, most of the cases it is a constant time taking the task. But when the collision occurs, collision means duplicate keys. When the collision occurs, it needs big O of n time operations for the collision resolution. Okay, so for avoiding this problem, okay, we are going to aggregate method. I think different kinds of methods are available, but we are considering that aggregate method. Okay, so in the aggregate method, is used to find the total cost. If you want to add a bunch of data, then we need to find the amortized cost by using a formula like cost of n operations. Means we need to search, say, 5 different elements. In the 5 different elements, 2 elements time complexity is big O of 1. The rest of the 3 elements time complexity is big O of n. At the time we need to calculate the aggregate of these 2. Means 2 into 1 plus 3 into n divided by overall n. That is the formula you are applying. So cost of normal operations plus cost of expensive operations divided by n. Suppose, very simple example is, suppose I need to search 2 elements. For one element time complexity is 1. Another element time complexity is n. So n plus 1 divided by n. Definitely the time complexity is reduced. Time complexity is reduced. That is the concept behind amortized complexity. Amortized time complexity. So the next thing is, so this is a one beautiful example to explain amortized time complexity again. So here, in a case of dynamic array, the items can be inserted at a given index is big O of 1. Means we need to declare an array dynamically. Means we are allocating the memory to an array dynamically. So we need to insert one by one element. So directly in the position we are inserting an element. So obviously the time complexity for this operation is big O of 1. Right? So that is big O of 1. But if the index is not presented in the array, it fails to perform the task in a constant amount of time. Suppose they are given an element but there is no valid index. At the time array bounds exception means one kind of segmentation fault may be occurred. Right? So for the case, initially double the size of the array and inserts the element. Means that when we are getting a false index, at the time, what is the solution they are suggested is, array size should be double and we need to insert the element. Right. So first initially they are inserting one element. Means allocating the size is 1. Only one location. And they are keeping the element 1 in that particular location. So next they are trying to insert the second element. So second index is not possible. Why? What to do? We need to double the size. So double the size, then inserting the element. Again, the next element, it takes only one time. But when we are keeping the another element, again also it takes 1 unit of time. When we are keeping this element, we need to double the size. That's why 4 locations are mapped into 8 locations. So here for 1 unit of time, here 1, but 2 takes more time, but 3, 4 takes 1 unit of time. When we are inserting 5th element, again it takes more amount of time. So that's why in this case we want to calculate the total cost for performing this task is C of I is equal to 1 plus, means initially we are inserting one element directly, so that results to 1. After that, based on the elements, means if I minus 1 is the power of 2. Why? Because here one element 2 power 0, 2 elements 2 power 1, the next third element 2 power 2. So each and every time you are doubling the power. That's why it means that I minus 1. So that will be calculated as sigma I is equal to 1 to n Ci divided by into n. Ci is nothing but cost of inserting an element for I numbers is n plus sigma log 2 of n minus 1 by 2, okay, j into z. So that is simply can be called as big O of n divided by n. Big O of n divided by n. So the aggregate method simply averaging of all the operations. By not considering one operation, whenever we want to do the subsequent operations. In the previous hashing case also, when we need to set 2 elements, when we need to set 10 elements. So what is the times, and total times are divided by with number of times operations you are performing. That is amortized time complexity. Next, asymptotic notations. So the asymptotic notations are used to represent time complexity of different behaviors. Different behaviors is nothing bad. So sometimes we are showing upper bound of the algorithm, sometimes we have to show average bound of the algorithm, sometimes we want to show lower bound of the algorithm. Right? So based on the times, means we need to show the different times. So asymptotic means the study of the function of parameter n, and n become the larger. What happens? Larger without the bound. Here we are considered about how the running time of an algorithm is increases with the size of the input. With the size of the input. Means for n larger values, what happens? For n smaller values, what happens? For n middle of the values, median values, what is the happens? Right? So generally an algorithm is asymptotically more efficient, will be best choice. Wherever we want to say the time complexity based on the asymptotic representation is the best choice to identify what is the upper bound, what is the lower bound, and what is the average bound of the algorithm. Right? So big O notation. Big O notation. Right? So the big O notation gives an upper bound of the algorithm. Big O represents upper bound of the algorithm. Means what is the maximum value. Right? And a function f of n, the upper bound f of n indicates the function f of n will be the worst case that it does not consume more than this computing time. Say for example, I am celebrating a function in my house. So maximum 500 people are not attended. That is the maximum. Why? Because I am given the invitations minimum 300. So I am approximating that maximum 500. So that's why based on the 500, I am giving the catering for 500 members. That is the mean of upper bound. Right. So the definition is the function f of n is equal to big O of g of n. F of n algorithm is equal to big O of g of n if and only if f of n greater than or equal to, read as f of n is equal to big O of n, if and only if their consecutive positive constants, we need to say this is the thing, f of n less than or equal to c into g of n for all of n greater than or equal to n naught. We need to say like this. That is definition. This is a purely mathematical definition. F of n is equal to big O of g of n if and only if f of n is less than or equal to c into g of n. These constants should be satisfied for n greater than or equal to n naught. From n naught means what is the starting value to satisfy this constant. When we are moving to the problem, you can easily remember the definition of big O. Right? So this is a small problem. This is a small problem. For example, f of n is equal to 3n plus 2. So I want to say 3n plus 2 is equal to big O of n. Means this is f of n, this is g of n. Right? So 3n plus 2 is a f of n value, g of n value is n. So shall I write like this? 3n plus 2 is less than or equal to 5n. Simply you can write 4n also, no problem. But here starting value is changed. Suppose here you are putting 4n, the n value is satisfied from 2 onwards. Suppose you are taking 5n, the n value is satisfying from 1 onwards. So substituting the n value, 3 plus 2, 5. 5 less than or equal to 5. Condition is true. Say suppose n value is 2, 3 into 2, 6, 6 plus 2, 8. 8 less than or equal to 10. Condition is satisfied. So the condition is satisfied from n greater than or equal to 1. So at this time the n naught value is 1. At this time n naught value is 1. C value is 5. C value is 5. So sometimes they are asking that f of n, or sometimes directly 3n plus 2 is equal to big O of n. Prove that. Means you need to prove like this. What is the f of n value, what is the g of n value, and what is the suitable constant to find out or to satisfy the given equation. What is the equation? F of n less than or equal to c into g of n. Right. So this is the answer. C is equal to 5, g of n value n not equal to 1. Therefore f of n is equal to big O of n. One more problem. Suppose f of n is equal to 20n cube minus 3, then prove that f of n is equal to big O of n cube. So, in this problem, g of n is equal to n cube. F of n value directly they are given that 20n cube minus 3. So, first of all, we are assuming that 20n cube minus 3 less than or equal to 20. How we are substituting 20? So here 20 is there. That's why I am starting from 20. Suppose 20 is not satisfied, then go for 21, then go for 22 like that. Right. So up to now, what is the range? The equation is satisfied from n greater than or equal to 1. The equation is satisfied from n greater than or equal to 1. Means that the c value is 20, n naught value is 1. So that proved f of n is equal to big O of n. So this is the way sometimes you are getting a mathematical kind of questions in this subject also. Prove it. Okay. This is about big O. So the next, just a sample example which are related to big O. Okay, this is called as sometimes what are the practical complexities or order statistics. Okay, so we are talking about big O of n. Computing time is constant amount of time. That is very less. That is the minimum. The next minimum is big O of n. Actually, big O of log n is there. Big O of log n. This is big O of log n is the logarithm. The next minimum. After that, big O of n is the minimum. That is called linear time complexity. Next, big O of n square. That is quadratic. Actually, after big O of n log n is called minimum. But after that, big O of n square. After that, big O of n cube called as cubic. Big O of 2 power n is called exponential. So this is the order. So the first big O of n is smaller. After that, big O of log n. After that, big O of n. After that, big O of n log n. After that, big O of n square. After that, big O of n cube. The largest one is big O of 2 power n. Right? So here one more problem is there. So for example, big O, f of n is equal to n cube of log n plus n square log n plus n log n. What is the time complexity of this one is, what is the maximum value, that is the time complexity. N cube log n. So that big O of n cube log n. Similarly, f of n is equal to n square plus n cube plus 4 power n. The time complexity is big O of 4 to the power of n. Why? Because the more value is depending on 4 power n. Why? Because we are talking about big O means upper bound. Means for n large values, what is the case? Okay? So the next thing is omega notation. So in case of omega, just see the definition. So the notation is used to find the lower bound behavior of f of n. So the f of n is lower bound implies that below that the time algorithm cannot perform better. It represents the mathematically by notation. Means that first the omega represents lower bound of the algorithm. Means it talking about minimum value. Right. So definition: f of n is equal to big O of g of n if there exist two positive constants c and l naught, if and only if f of n should be greater than or equal to c into g of n, n greater than or equal to n naught. This is the case. Suppose this is an example. F of n is equal to 3n plus 2. Same kind of thing. Right. So we need to prove f of n is equal to omega of n. So here lower bound means that we are substituting that here at this time 3 only. 3n plus 2 greater than or equal to 3n. So here f of n value is 3n plus 2, g of n value is n. So the c value is 3, n naught value is 1. This is true for all the cases. Alright. Next, in case of f of n is equal to 50n square plus 10n minus 5. That is f of n value. What we want to prove? Omega of n square. Means that g of n value is n square. Again we need to substitute 50n square plus 10n minus 5 greater than or equal to 50n square. So where it is proved? And from n greater than or equal to 1, it is proved. Right? So the c value is 50 and n naught value is. So like that, we need to obtain the lower bound of the algorithm also. Means what are the minimum values? For minimum values what we get. That is omega refers to lower bound of the algorithm. So this is the last notation, theta. I think other than this, two notations also there, but that is not important. So theta notation. So this is theta refers to average bound of the algorithm. Omega represents lower bound, big O represents upper bound, theta represents average bound. Okay, so the lower bound and upper bound may be same. So big O and omega will have the same functions. For example, finding the minimum and maximum of an array elements, computing time. Means we need to find out the maximum element or we need to find out the minimum elements. The time complexity is big O of n and omega of n. So big O of n represents the upper bound, omega of n represents lower bound. So there exists a special notation to denote the functions having same time complexity of lower bound and upper bound. Notation is called theta notation. So where the functions are exhibiting the same kind of time complexity with reference to lower bound and upper bound, then theta is comes into the picture to represent the average time complexity. So f of n is equal to theta of g of n. If there exists no positive constant C1, C2 and m0 with the constants that C1 into g of n less than or equal to f of n less than or equal to C2 into g of n for all of n greater than or equal to m0. N greater than or equal to m0. So, first example, f of n is equal to n square minus 3n should be proved as theta of n square. Next, f of n is equal to 3n plus 2. I already seen theta of n. So here you clearly know. So in case of 3n plus 2 we have proved as big O of n, and in case of 3n plus 2 we already proved as omega of n also. The two things here you want to substitute. So what is the thing you want to substitute? So here C1 into g of n. What is the g of n value? Here two kinds of g of n's are there. Right. So 3n less than or equal to 3n plus 2 less than or equal to 5n. The value true should be n greater than or equal to 1. So that's why we go of means theta of. So this is the kind of implementation we done in case of omega. This is the kind of implementation done in case of big O. The two things are mapped together, we proving the theta notations. Next, f of n is equal to 10n square plus 4n plus 2. That is called theta of n square. F of n is equal to 10 into log n plus 4. That is theta of log n. Theta of log n. So, this is about three kinds of asymptotic notations. One is big O represents upper bound of the algorithm, omega represents lower bound of the algorithm, theta it represents average bound of the algorithm. Apart from these, two things are also available, that is little o, little omega. But those are not that much important, we are not talking about at this time. Okay? So, summary. So, what are the things in the today's concept is, the first we are talking about time complexity. So, to find out the time complexity, here two different kinds of methods are there. One is recursive substitution method. So, count is a variable. The count variable we are substituting recursively. That is one method. Another one is called as step count method. Another one is called step count method. So those two things are discussed for 4 examples. One is a very simple, and another one is addition of an array, and another one is addition of 2 matrices, and the next one is Fibonacci. The second one is asymptotic analysis. Asymptotic analysis. So here only we have discussed about amortized time complexity also. In the amortized time complexity, we have discussed what is the aggregate method. Aggregate method. So in the next session, we are discussing about what is the performance measurement, that is the one, and next we are talking about the other kinds of asymptotic notations also. Thank you.